once you're in it, you're in it. And you've got to go all the way to the end. Because you commit yourself to such a level where there is no compromise. You give everything you have. Everything, absolute everything.
Dear ladies and gentlemen, dear sponsors and partners, Formula student community, family and friends. Welcome to our 2021 rollout here in the BMW Group Brand Experience Center in Dielsdorf. Hi, it's an honor for me to welcome you to this venue. My name is Jan Burnett and I'm the CEO of both AMZ racing teams. Tonight, we'll present you both new prototypes of the Academic Motorsports Association in Zurich, on which our students worked hard and are time pressure and astonishing motivation. We will start with an introduction to general concept and the newest innovations before going over to a driving demonstration on the parking lot in front of the building. I am generally grateful for the opportunity to have this event here today. Being able to show our work live to you, dear audience, all while having our online public close to us as well with the interactive live stream is an important step for us towards the races this summer. We worked hard to make this an experience for each one of you. So tune in, turn up the sound, and share our excitements during the various videos. Next, I'd like to hand the word to our host today, our main sponsor since our first electric car, Furka, in 2010, the BMW Group. I welcome Nicolas on stage.
Thank you, Jan. Thank you very much. It's a special honor for me as a manager of the BMW Group Brand Experience Center, to welcome you tonight in our event center in Dilsdorf. A hybrid event, as Jan just mentioned, with an audience here with us and an audience from home. A good example of how we need to constantly adapt our business as an event center in order to always fulfill the expectations of our customers. This is possible by staying innovative. Innovation is a key word for both BMW and AMZ. By BMW, the innovation is important in the product development, but not only. It's also very important in the way we communicate with our customers and partners in order to keep track on the relationships with them. The relationship with AMZ is based on trust and passion, and it started 11 years ago. Congratulations to AMZ for the extraordinary results on the tracks. BMW is very proud to be with you, along with other partners and sponsors, and to be part of a great story written by one of the best teams in the world of this motorsport discipline. I wish you all a great evening with us. Thank you.
Thanks a lot, Nicolau. I want to come back to something that we are especially fond of this season: the support we were given from all our sponsors. We had our parts milled, printed, our rotors balanced, our monocoque painted, and our standards elements delivered. Even with the general difficulties in industry, we got all the assistance we needed to carry on. Work continued at home or was rescheduled and reorganized. Online meetings started to show their benefits and downsides. After the first lockdown passed, we finished assembling our electric race car and had our first drive, our shakedown, on the 24th of July. During summer, we tested the various subsystems before starting with the next team in September to rework the general design and introduce new performance-enhancing concepts. Finally, coming back to what we are here for today, I want to raise your attention to the presentation of our newest electric prototype before going over to the presentation of our next generation autonomous race car. Enjoy.
Armed.
Should work.
Hello and welcome to the rollout presentation of the AMZ electric team. My name is Tobias. I'm part of the controls module of this year's electric team, and I would now like to bring some key aspects, some key technical aspects of our newest car, Alvier, closer to you. Starting off, the base structure and also the largest component of our newest car, our one-piece carbon fiber monocoque. With the help of our lap time simulation, we were able to take into consideration different key aspects, such as, for example, the weight, the center of gravity, and also aerodynamic characteristics, to then, in the end, find the best possible combination of these to build the best possible monocoque. Assembled from a sandwich structure with a honeycomb aluminium core, we were able to reach maximum stiffness and strength for every possible load case. In addition, an overhauled packaging concept allowed us to optimally segment the key components and therefore make it very maintenance friendly, which reduces the time to adjust settings and make repairs. I would now like to move on to our tractive system. In order for alvier to actually drive, we need a tractive system, of course. This consists of an accumulator, inverters, and motors. The first of the three subsystems is our high voltage accumulator, which delivers the necessary power to our car in order to perform as required. It is also the heaviest component of the car. The 19 sub-packets enclosed in a Kevlar composite box deliver the necessary power to all the motors so that they can operate at their physical limits. Thanks to our optical accumulator management system, we can monitor all the voltages and temperatures of the different cells while having it free from electromagnetic interferences. In order to transform the direct current from our accumulator into alternating current, we need an inverter. In the third generation of our in-house developed AMZ inverters, we were able to overhaul the packaging concept and include state-of-the-art components such as silicon carbide semiconductors. With those, we were able to cut down the weight massively compared to commercially available solutions. Thanks to high-speed gates, we can reach switching frequencies of up to 100 kHz, and optical fibers ensure an error-free communication. With the help of our two dual inverters, we're able to recuperate more than 60% of our accumulator capacity. Last but not least, the third of our three subsystems are our 10th generation in-house developed wheel hub motors. Each motor weighs in at 1.9 kilos and delivers a peak power of 40 kilowatts, which converted is more than 200 brake horsepower for the entire car. With torques of over 20 Newton meters, we're able to push the boundaries of acceleration to a limit. A carbon fiber sleeve ensures that the magnets stay attached to the rotors, even at rotational speeds of 28,000 revolutions per minute. Moving on, I would like to switch away from the tractive system and go into the direction of our wheel packaging. This encloses all the parts which are necessary to actually transduce the power onto the ground. We had quite a challenge integrating not just a motor, but also a gearbox and a braking system into the limited space of our 10-inch rims. However, thanks to our integrated stage planetary gearbox and a transmission ratio of more than 17, we were in the end able to go for faster spinning motors. One key component of the wheel packaging is also our upright. It transduces the power onto the ground while holding up against the developing loads. The topology optimized part was manufactured through selective laser melting of aluminium. Thanks to this process of additive manufacturing and topology optimizations, we had massive design freedoms and were able to, for example, integrate the cooling channels directly into the part. Moving on from here, I would like to hand over to Maurus to lead you to the second part of the presentation.
Thank you, Tobias. Hi, my name is Maurus, and I'm also part of the controls module this year. The basis of vehicle dynamics is the suspension on the car. It allows us to design the car to behave in transient phases as we desire. So this means in cornering or acceleration and deceleration. This season, we opted for a hydraulic pushrod-based suspension with mode decoupling for roll and warp modes. In tight collaboration with an industry partner, we were also able to develop a new rubber bump stop, which allowed the suspension to have the softest springs in AMZ history, improving the performance drastically. We are also especially proud that we were able to implement an actively controllable ride height, allowing us to gain the optimal performance out of our aerodynamic undertray, as well as a rear-wheel steering system, allowing us to increase our cornering velocity. With the switch to a smaller tire came the challenge of developing a new carbon fiber rim. After 2 years in development, the finished product impresses with a weight reduction of 50% while providing more rigidity than a commercially available aluminum rim. The carbon fiber reinforced polymer structure uses a ROA-cell core, which is reinforced with aluminum inserts if needed. We also completely redesigned the workflow around our computational fluid dynamics simulation. It allowed for a maintenance-free development of a full aerodynamics package, which includes over 20 airfoils. There are multi-airfoil rear and front wing, side pods, and a drag reduction system. The carbon fiber structure weighs in at only 11 kilograms and outperforms any previous aerodynamics package in the ratio of coefficient of lift to coefficient of drag. To not be limited by the heat losses of our traction system, we also reimagined the whole cooling system of our car. All parts in our cooling system are a stunning demonstration of selective laser melted aluminum parts using topology optimization as the key design aspect. Our first generation air-cooled upright is able to match the water-cooled version in weight and performance while being designed rather conservatively. So in future iterations, huge weight savings are to be expected. Our newly designed radiators are able to outperform a commercially available radiator with the heat transfer per kilogram ratio by over 100%. All aspects of the cooling system were also carefully placed using our computational fluid dynamics simulation to work hand in hand with our aerodynamics package, resulting in an increase in coefficient of lift of 0.1. In tight collaboration with the students from the University of Applied Sciences in Lucerne, every printed circuit board, apart from the electronical control unit on the car, is self-developed by AMZ. This allows us to control over 200 individual sensor signals on 4 independent CAN buses and keeps the unnecessary hardware to a minimum. An increase in battery voltage also allowed us to decrease the diameter of our high voltage cable, resulting in a weight reduction of over 20% in all our high voltage cables. In especially hard to reach places, we implemented flex PCB technology, keeping cable weights down and keeping also the maintenance time down. With our control system, we opt to give the driver the best driving experience possible. With a newly fitted tire model, we were able to implement an even more accurate version of direct torque vectoring and traction control, giving the driver the best performance possible. This year's control module also implemented a new data analysis software, which allows every team member to do basic data analysis without any coding experience. And last but not least, the control module finalized and validated the lap time simulation used to compare setups in engineering design. This should provide the best setup decisions for years to come. Before we unveil the car, we would like to show you a quick video shot during manufacturing and assembly of alvier. Please enjoy.
Girls with their nails done now. Girls with their nails done. Girls with their nails done. Girls with their
Now, the moment you've all been waiting for, the unveiling of our 14th car, Alvier.
I think now you can go next until just the video.
Hi, my name is Costanza, and I'm a core team member in the operations in Driverless division. Tonight, I will walk you through the Driverless project here at AMZ. With the introduction of the Driverless class in 2017, AMZ took up the challenge and tried to upgrade the 2015 electrical Fuela with software and hardware for the Driverless challenge. Since then, we also followed up with Gotthard 2018 and with Pilatus Driverless in 2019. But what does it actually take for these cars to become high-performance autonomous race cars? We start off with state-of-the-art sensors. We add LiDARs, which are laser measuring sensor devices that can measure distances between surrounding objects very, very precisely. And we also add the GNSS system to precisely perceive our position in space. Finally, we also have cameras in order to perceive the complete field of view. To replace the driver steering movement, we installed a steering actuator directly behind the steering wheel. And to ensure the safety of the vehicle at any point in time, we have an emergency brake system, which is installed behind the pedals. It can be activated at any time from any distance, and it brings the vehicle to a complete and safe stop when needed. In addition to hardware, we also need to include our driverless software, which ultimately converts sensor data into motor torques. And this is contained in our computer box, which is at the back of the car. And the computer box includes a processor and a graphics card. And it is able to process the output of our sensors in real time and also run our algorithms. Here tonight, we present our driverless car for this current season, which is Pilatus Driverless 2021. As it is a car which comes with a great legacy, I'd like to walk you through its history. Originally, Pilatus was developed back in 2017 by our electric team, and it competed in Formula Student electric competitions. Already as a non-autonomous race car, Pilatus achieved 2 first positions in FS Austria and FS Spain, and a 2nd position at FS Germany. Then, Pilatus spent the following year featuring in exhibitions and events around the world. It inspired the young minds and also served the community with our learnings and innovations. Some of the features events that we participated in were Formula E in Zurich and the Auto Salon in Geneva. In 2019, Pilatus then became driverless for the first time. Within 1 season, the 2019 driverless team designed and incorporated the driverless hardware while also writing the software to bring Pilatus Driverless to life. That same year, the team competed in Formula Student driverless competitions and excelled in both competitions they attended. Since the start of 2020, we have been continuously iterating on Pilatus's both software and hardware to this very day. Many challenges were overcome by the team, but it is safe to say that with Pilatus Driverless 2021, we now have the fastest autonomous system in the AMZ history. As we are now ready to compete in summer challenges, our autonomous system must succeed in 4 different racing disciplines, each coming with its own challenges and peculiarities. We start off with skatepad, where the car needs to drive on a route shaped like an 8, and is trying to strive for the absolute limit of lateral acceleration. We then follow with acceleration, where the car needs to complete a straight 75-meter stretch as quickly as possible. And we then went on with autocross and track drive, where the car needs to drive on a route. And I will now hand the word back to Ben so that he can explore more in detail these 2 disciplines.
Thank you very much, Costanza. Ladies and gentlemen, friends, I'm Ben. I'm the CEO of the AMZ Driverless team. And now I want to talk about autocross and track drive, as Costanza said. So autocross and track drive are the 2 more challenging and 2 more interesting dynamic disciplines in the Formula Student Driverless competition. Later, when you guys go outside and see the demo of Pilatus, we'll actually also be demoing autocross and track drive, one after each other. And so that's why I think it's important to tell you a bit and give you an insight about what these disciplines actually are, and also to give you an overview of what the underlying engineering problems are. So stay with me, and let's get started with autocross. Autocross and track drive are simple to understand. In autocross, the goal is to drive 1 lap on an unknown racetrack. After autocross follows track drive, and here the goal is to drive 10 laps on the same track as an autocross. Now, on first sight, you may say, these 2 challenges look very similar. They're unspectacularly similar, but in fact, they're rather different engineering challenges, and I also want to get to why that is later on. So before talking about the autocross software pipeline, I first want to introduce this basic concept regarding autonomous mobile robots. First, an autonomous mobile robot needs to perceive its environment, and it does this through sensors. These sensors give us data, and then we need to process the data, or the robot needs to process the data to make sense of it, make informed decisions, and take action. By taking this action, the environment then changes. The environment perception of the robot changes, and this closes the loop. So this is the basic perceive, think, act model. And now let's use this model to understand better what it needs to design the autonomous system of an autonomous race car. So what we want from the race car is pretty obvious. We want it to drive the fastest. And this is determined by the correct motor torques and the correct steering. The perception that we get depends on the sensors that we implement. And the thinking part are our algorithms. It is the function that translates and transforms the input data to the correct motor torques and the steering. So now I want to talk about the perception part of the autocross pipeline. The most relevant 2 sensors are the LiDARs and the cameras. We have 3 cameras from Basler and 2 LiDARs from Hesai, one 20-beam and one 64-beam LiDAR. And in this video, you can see the point cloud, the points from the point cloud projected into the images using accurate LiDAR to camera calibration. And each single one of these red dots represents 1 distance measurement from the LiDAR. Now, after perceiving the environment, we need to make sense of it. Pilatus needs to make sense of the environment. It needs to detect the racetrack. So here the task is, or the question is, how do we teach a machine to detect a cone, to know that the cone, and to also know that the cone marks the racetrack? And our perception team uses artificial neural networks for this. They implement machine learning algorithms to be able to detect the cones on the racetrack, to be able to differentiate them from other objects like humans, grass, and so on, and to be able to detect their position. And after detecting the position of the cones, we can then sort them into a left and right boundary. Following comes the control algorithm. So given the 2 boundaries that we've just calculated, we can then, the control algorithm then calculates the locally optimal race line. It subsequently also calculates the correct motor torques and steering necessary to follow this race line effectively. And all of this calculation needs to take into account the specific vehicle dynamics of Pilatus. So here in the next video, you can see the controller in action. This simulation here feeds the left and right boundary into the control algorithm, which then calculates the locally optimal race line in green, and also the correct steering commands and motor torques. And this vehicle model, we have a computer model of our car in the simulation, and this is what you can see driving here in this video. So this was a very high-level overview of our autocross software pipeline. And now I want to invite you everybody to take a step back and think again about our two disciplines that we have. So obviously, we could also use the same software to run track drive. But we don't do this because there are better methods. And in fact, most Formula student teams, they use the other method. So I want to introduce you to this. During autocross, we run this so-called simultaneously localization and mapping algorithm. And what this does, it takes the cones that we perceive as landmarks, and it builds a global map out of it. Using this global map, we have basically all the information about our racetrack layout. And based on this, we can also pre-calculate the globally optimal race line already. So you can see that our premise for track drive is very different than in autocross. Here we already have a full map of the track layout, and we have pre-calculated the globally optimal race line. So the focus of the software here is also different. Instead of focusing on long-range perception, instead of focusing on long boundaries, here we focus on accurate localization. So we need accurate and robust perception, which gives us this accurate and robust localization. And with this localization, the track drive controller can then best follow this globally optimal race line. So in October 2020, Pilatus was already able to show that it was on par with a Formula 4 race driver. And in future, we want to win the season's competitions, obviously, and we also want to continue pushing for the superhuman racing capabilities of Pilatus. And with this, I hope that you have a bit of a better understanding of what's going on later outside when you go outside and see Pilatus run. And with this, I want to give the word back to Jan.
Thanks a lot. It's such an important milestone in a project to show your work, to show what you have where you have put your energy in all year long. To put our ongoings into perspective, I want to introduce you to this typical season of ours. Beginning with team building and first introductions, in the new teams, both the electric and the driverless one, get to understand the most important theory on race cars. They start into the development of a new main concept for their car, respectively their autonomous system, right after. Next is the manufacturing and commissioning phase, before testing starts in summer. After a successful rollout, they are pushing hard towards summer for the races planned all across Europe. From getting up at sunrise, preparing for a day on the testing track, to working on the latest newsletters, the tasks of our team members are manifold. Starting with some early calculations on their design choices for their respective system in October, our engineers eventually end up getting experience in every kind of task by the end of the year. All of this while our marketing team kicks off the season with setting up plans for our social media accounts and new partnerships, and end up organizing a big event like the one today. This journey is made possible with the active support from our alumni, as the further success of AMZ all comes down to an efficient and thorough knowledge transfer to the next generation. Our leads, in contrast, both technical and operational, have the possibility to acquire hands-on know-how in leading teams and coordinating tasks, after having gained valuable experience on the car for a year or two. Motivating, teaching, and listening to the people in your model. In short, having the responsibility for others adds a new challenge for them again. But what is the qualities that our team members bring to tackle a project like ours? Initiative, passion, a broad variety of skill sets, an open mind, creativity in team building, and respect for their friends to be. Everybody brings something different, but everybody adds something important for a successful team. At the end, you're pushed out of your comfort zone, and that's where the learning happens that no lecture could ever replace. This year, we have had the great opportunity to move to our new workshop provided by ETH in the Innovation Park in Dübendorf. Working alongside other teams competing in different fields and all the necessary facilities in one place will help us to kickstart next season. And we are thrilled to present you another fundamental change in our project. Starting next September, AMZ will only build one single car. In fact, both the development for a driverless system and the design of a new prototype are merged into one single product to fit the new format of the races. Yet, as the proverb says, a picture is worth 1,000 words. I don't want to keep you tangled to my words any longer, and thus let you discover what's the real drive behind each one of us. Experience what it's like to be part of the team with our last video today before the show run.
I think it's hard to define where passion comes from. I have always been very passionate about two things: engineering projects and teamwork, working with friends. And this is basically what you do at AMZ. These are the grounds of AMZ. We're building something that performs at a world-class level, with people that at the same time you're having fun with. This is all I can ask for, at least. Very special thing about AMZ is that you get to follow the entire process from building an idea in your head, which can be practically anything. The possibilities are quite endless. And you follow the entire process during the entire season until you actually see it running in the car in real life. And you see it performing. It's not just an idea, it actually is happening.
Probably my greatest achievement here at AMZ, which I'm proud of, is to have provided the new team members with the same environment and resources that were provided to me when I first joined the team, and see them thrive and grow and see them achieve basically more than I could achieve. Probably the best part about being here at AMZ is to work with some of the most talented students and to get to work with technology that you would never have been able to work with anywhere else. I think joining on a Formula student team, no matter which university you are in, is probably the best opportunity you can get to gain practical knowledge, to put all the things you learn in your studies to a practical task and see all the work you put in, all the sleepless night, and see that result in something that is a car that drives, and it's super fast.
My biggest motivation was being able to see the car drive in the end. So just to have your work being on a track and racing against time, that's really, really rewarding.
Okay. Down.
Ready? Yep. 1, 2, 3. Like this. Down? Yeah, down. Okay, this one is loose.
AMZ requires a lot of hard work, and just the passion comes when working with a team and everybody has the same goal, and that really gives a lot of passion and motivation. Unfortunately, in my year, we were not able to go to the races, so I'm really looking forward to see what this year's team can do with the car that we built over 2 years. During the studies, we learn a lot of theoretical concepts. In AMZ, I was really able to apply those concepts and to take all the resources we were given and to really work as an engineer, and it really made me a better engineer.
The main thing I'm grateful for are for my teammates, how they sacrifice their personal matters and maybe even their studies to be here every day in the workshop to actually make this happen. Because this is not possible without the 100% effort of all the people doing this. That is the number one thing I must say that I am grateful for. And of course, I am greatly thankful for all our sponsors and partners, without whom this project wouldn't even be possible.
Thanks a lot for your attention. We're glad you're here or you're in our live stream. From now on, we will split up. The live stream will go to the Q&A in a few minutes. And for the audience here in Dielsdorf, I welcome you to get up row by row, start in the back, and go to our racetrack in front of the building. Keep your distance, wear your masks, and see you outside. Thanks a lot.
Hello and welcome everybody to our little Q&A. my name is Christoph. I'm from the electric team. This is Eloy, also from the electric team, and Stefan from the Driverless team. We're here to answer your questions if you have any, and we hope we can answer your questions.
Perfect, thank you. And thank you everyone who sent and is still voting questions on Slido. I think we have a very interesting one for start that everybody is up voting. So Stefan, maybe you can answer to us, how far is our driverless team from beating a human race driver?
Yeah, so I think in driverless it started very slow, and we've made some really big leaps now. So last year we were for the first time able to really get quite close to beating a human driver. So if I have to give like a personal prediction, I would say 2 or 3 years I think can beat the human driver.
Thank you, Stefan. Maybe we'll start with asking to electric. If we put our 2 cars that we presented today, alvier and pilatus driverless, against each other, who would win? In which discipline would alvier win?
I think alvier would probably win about in the autocross and track and endurance. I think you got us on acceleration because you have no driver in it, so you're far lighter than we are. And acceleration is easy for driverless, maybe. I don't know that much about it. Yeah, but I think we're very good. Both cars are very good cars, and if you put 2 drivers in them, they would most likely be as good as each other. Like there would be no difference. I mean, how is it without the driver? You think you could beat us?
I mean, in acceleration, I agree because we are not having the driver mass. But in the other disciplines, at the moment, you should be ahead. But yeah, I think it's going to come. The switch is going to come in the next years.
Definitely, we have all summer to prove ourselves in both areas. So let's see what happens.
And we'll see next year with the merge.
Definitely, definitely. Okay, question for driverless. Stefan, what's the most important sensor on the driverless car?
So, I mean, there's 2 main sensors. It's the camera and the LiDAR. And it's tough to say most important. The LiDAR is super useful for very accurate positions, which especially in a less developed system is very, very useful. But the downside is it doesn't give as much color information, and color is very good to know the boundaries, what is left and what is right, and actually find the path. So I'd say in the beginning LiDAR is a bit more important, but the more advanced our algorithms get, the more importance the cameras are going to gain, because our machine learning algorithms are getting more advanced, and we less and less depend on the really high accuracy of the LiDAR, I would say.
Perfect. All right, so this is probably a question for both teams, a bit mixed. How many team members we have? So can we start with electric?
So in electric we have around 25 team members consistent of the focus students, which are students from the ETH 3rd year. Then we have the freelancers, students from the 2nd year, and then we have like our alumni, we have a very active alumni base. I think around also 10 to 15 students who did the project previous to us and are still helping out in any team roles, etc., like you are doing right now with us. And driverless, I think you have mostly master students, but how many do you have?
Yeah, mostly master students, and we have around 10 core people that are really doing like all the programming, making sure the car runs, and then also like 1 or 2 freelancers. But the really important part is the alumni. So the people that have done the project in the past, and they have such an amount of knowledge distributed over all the people. So that's really the key, I would say, to AMZ's success.
Definitely. So all right. Yeah.
Are the drivers also students?
This is actually enforced by the rules. So by regulations of our competitions, we have to have our drivers being first non-professionals drivers, and second being university students. So definitely they all are. Yeah. Okay, back to driverless. Everybody has a lot of interest on the driverless technology, which we also do, obviously. So what's a prerequisite knowledge for joining driverless? I guess a lot of students would like to join, but they don't know if they're ready for it.
Yeah, so I would recommend anyone to apply, because there is no prerequisite knowledge. Everyone will bring in different types of experience, so some will have more programming knowledge, some will have very little or even none at all. But it doesn't matter, because what really will matter is how motivated you are. And you can learn anything during the project, really.
Exactly.
So definitely I encourage everyone to apply Yeah.
Yeah, that's the same case also for the electric team. We encourage everybody who is able to join us for the Focus project, or as a freelancer, what we call the people who are not earning credits for participating in the electric project, to join, because this is an educational project at the end of the day. And we hope that our students can learn a bit more sensors. Let's see what is the next thing that people want to know is how big is the sensor in your camera, and their suggestion is 1 inch.
Okay, to be completely honest, I don't know this. I didn't work on the cameras, so I don't know.
We unfortunately didn't bring the data sheets here, but come to our box in the events as long as the Corona regulations allow, and you can take a look by yourself. Okay, more cameras. How do you process all the cameras at the same time?
Yes, at the same time. So we have global shutter cameras, first of all, which means that they capture all the pixels at exactly the same time. And we have front, left, and right cameras, and we process them in parallel. And now a question for you guys: which parts of the car are manufactured by the students?
A lot of them. I think the biggest part of our car, the chassis, is totally manufactured by students. So we start manufacturing this in January, and our goal is to stop manufacturing it in March, middle of March, end of March. And mostly all of the carbon parts are manufactured in-house by us, and also some minor milled parts we do in-house, but milled parts are mostly done by our sponsors, which very genuinely support us in that category. Yeah. And how do we keep progress in the team and transfer knowledge to future generations while building the new car? I think you can tell us a lot about it, since you did it this year and in the previous years as well.
Yeah, it's always a big challenge that we have in this team, that our core in both teams starts from the ground. So it is not expected that they bring some experience. So we have to educate them on how to build a car from scratch. And we have to build a car at the same time. So we have a set of tools. We have our own internal Wikipedia. We have a calendar that includes meetings with our veterans. Our module leads and team leads tend to be previous students that have participated in the couple last seasons. So all these measures allow us to transfer the knowledge in a fluid way, or as much as it's possible. And alternatively, we offer them coffee in the office to tempt them to come inside and comment on what it's going.
That's the reason why you stayed, right?
Yeah, definitely. All right, a question about university support. How are we supported by the university?
I mean, I would say the most obvious example is the office space and the workshop space. So these are already huge factors. Nothing would be possible without this. And otherwise, also the professors and PhD students, we can do thesis, master thesis, bachelor thesis with them, which is very, very useful. And they can also pass on their expertise in these areas to us. What about the electric?
And the electric team?
Almost the same with you. We share an office space and we share a workshop space. So I think I can only talk about that mostly. Also for our bachelor thesis and master thesis, we can do with the project. And we also have a lot of help from professors and PhD students if we have any questions, and a lot of support from ETH there.
Yeah. All right, a question about motor. Christoph, do you feel like answering this one? Do we test our motor in a dyno bench to check the efficiency?
Yes, we have a self-developed motor test bench where we test our motors, and we test our efficiency with I think you can tell us more about it because you did the motors 2 years ago. But we test our motors with different measurements, like oscilloscopic measurements from the electric side and also from the heat side, like how much losses do we have with our motors. We have sensors in the water which measure the flow and the temperature, so we can see how much losses we generate and how efficient our motors are.
Yeah, we definitely focus a lot on validation, but at the same time we have to be realistic with what is achievable, so we still rely on the simulation and the analysis that we do of our parts. I think we're running out of time. It's time to see what the cars can do on the track. So we hope that you enjoyed this time with us answering some questions. Visit us anytime, get in contact with us if you have any questions, and otherwise we hope that you enjoy seeing our cars on the asphalt. Thank you very much.
Hello, good afternoon. Welcome, everyone. In first place, allow me to give you our warmest welcome and thank you all of our sponsors, friends and family, and all of the people who are watching us live right now in the live stream. Thank you for staying with us in this very special rollout day. My name is Adrià López Escoriza, and I am a member of AMZ Driverless, and I will be the moderator for this live demonstration today. Now we're going to get started with a live demonstration of Pilatus Driverless, where you will see the car perform a show run in 2 different modes. Firstly, emulating the real Formula Student competition, we will start with autocross. In autocross, Pilatus has to perform in a track that it has never seen before. It will be using all its vision sensors and algorithms to detect the cones that form the limits of the track. We'll start with a slow run, and then the dynamic team will then gradually increase the speed for a higher performance. The reason for starting with a slower run, as my colleague Ben introduced, is so that we are sure that the car captures all the details of the track, so that later, using all this data, we can recover an accurate map of the track thanks to our mapping algorithms. Then, with this map, we can extract a trajectory to optimize the lap time for the track drive demonstration. In second place, in the track drive demonstration, we will push a little bit further the capabilities of Pilatus. We'll perform a series of consecutive laps at high speeds and finalize with an emergency stop to give an end to the show run and hand over to Alvier. I am sure that the car will be ready to go in any minute, so I'm going to start stepping away from the track. Thank you very much. Okay, so now the car seems to be ready to go. The autonomous system responsible, the person with the big box attached to his waist right there, has already started the startup sequence, and Pilatus is performing all of its safety checks before starting. If everything goes all right, we will now see the light above Pilatus, which marks the tractive system or high voltage system activation go from green to blinking red. As we can see right now, it just happened. And the lights on the side just went orange, which marks the activation of the autonomous system. And we only need now the remote emergency system signal, which was that, so that the car can start driving. Okay, so as you can see, the car is now performing in autocross mode. Some other details about the specific algorithms that we actually use in this mission. The car is now running in what we call exploration mode, which means that it plans its trajectory as it receives information from the perception algorithms. The perception algorithms detect all the cones of the track and pass the information about their position, color, and even uncertainty to the estimation algorithms. That is where we try to make some sense out of these unconnected inputs. For example, connecting all of the list of cones that were passed and extracting meaningful boundaries for the controller. The controller then plans a trajectory ahead, and finally outputs commands for steering and throttle for the 4 motors to stay as close as possible to this optimal trajectory you computed beforehand. This way, we managed to minimize our lap time in autocross, therefore achieving a higher performance for the competition. If you let me talk a little bit about our dynamic team today here on the track, you can see, for example, our dynamic team below the tent. They communicate lively with Pilatus, tuning its performance in real time, thanks to our bidirectional Wi-Fi communication with our monitoring station. They control parameters like the velocity limit of Pilatus. Right now, we have an 8 meter per second constant velocity limit, which is the velocity at which Pilatus is performing right now. Additionally, we have a responsible person for monitoring the state of the car at all times. Our custom monitoring software allows us to remotely check the state of almost all the systems of the car while the car is driving. From the running frequency of the algorithms, to the air pressures of the emergency brake systems, to things like how many cones Pilatus is seeing at this moment. This enables us to make sure that the car is safe at all times during the run and to actually understand what Pilatus is seeing and even thinking at all times. So right now, our dynamic team has just increased, or will just increase in a few seconds. You just saw it there. The velocity limit to 9 meters per second, pushing a little bit farther the performance of the car. As you can see, already a much smoother trajectory can be observed. And finally, that last push you saw right there was our dynamic thing increasing to 10 meters per second, which is the performance that we're seeing right now. Not only we can tune the velocity limit specification from the monitoring station, we can tune much more parameters of the controller to, for example, make it more aggressive in the turns, as we may see in a few moments, or even to make it start side slipping. If you allow me to introduce a little bit more of the dynamic team that we have today here on track, we have the autonomous system responsible holding the big red button over there. That is the remote emergency system. This person is responsible of determining if the car is in a safe state to drive in the electrical and autonomous side. In addition, he's also responsible, as I said, for the remote emergency system. If the car shows an unusual behavior, which we'll hope not, or he sees something that is not quite right during the run, he will immediately press that button he's holding to activate the emergency system and make the car come to a safe stop. At the same time, the remote emergency system has the last word before the car starts driving. Even when all the manual checks are done, the system gives the ultimate go signal before the car starts driving. Also, we have our track marshals, which are the rest of the people with the vest that you can see distributed along the track. They are distributed this way so they can control the car from different angles. If they see some odd behavior, they will use the radio to request an immediate emergency stop to the autonomous system responsible. As of now, the car is running at almost a constant speed of 10 meters per second. We'll perform a little bit more laps in this show before moving on to the next mission, track drive. Some interesting facts about Pilatus, for example. It was built in 2017 as the first electric car, hydraulic and decoupled suspension, the former student world. Okay, so now the car has come to a safe stop, and finally the emergency system has been triggered. As you can see, the autonomous system state indicators were blinking blue with this beeping sound. And the emergency brake system was also triggered, releasing as much pressure as possible into the brake lines to make sure that the car came at the safe stop as soon as possible. Okay, since we have run for some time now, the dynamic team will change the mission to track drive. For this, we will turn off all the systems in the car except the low voltage system, which has to remain active so that the team inside the tent can remotely connect to the central computer. The low voltage system actually powers everything in the car that is not part of the tractive system, from the pumps for the cooling system to the autonomous computer, going to all the sensors like the LiDARs, cameras, or even the velocity sensors. Therefore, Okay, now the autonomous system responsible has selected the mission for truck drive, and we will start the startup sequence at any time. The startup sequence actually consists of firstly activating the tractive system, which is what we see when the truck active light situated on top of the car goes from green to blinking red, as we saw before. And then the autonomous system gets activated, which is marked by the autonomous system state indicators located at the sides of the car, and it's the bright orange we saw while driving, and then blue when we emergency system. So now the tractive system button has been pressed. Safety checks for the emergency brake system done before the car can actually start running. For the checks of the emergency brake system, the car checks if the brake pressure, things like if the brake pressure in the lines are high enough before we can start driving, to ensure that we have enough braking force to stop the car in the event of an emergency. So now the car has started the truck drive mission and seems to be quite cool. Some other technical details about the truck drive algorithm. For example, since the car already has a map and a computed optimal trajectory for the truck, the job of the control algorithms is to stick to this trajectory as faithfully as possible to minimize the lap time. The perception algorithms are still running the cones and help the car localize in within the track, which is crucial for the controller to know which part of the trajectory it has to follow. Some other interesting facts about the truck event itself. It is the highest value dynamic event at the Formula Student competition, with a total points of 150 overall. Events competition is 550 points. It is the highest value.
Going to 9 meters per second.
Sorry. It is the event actually that allows the team to show its highest performance, since the map is already computed. Apparently the car hit a cone right now, which is a normal behavior sometimes. Of course, we will tune this behavior before the competition to ensure that it doesn't happen. We still have some 2 months or a month and a half of polishing to be done. As this behavior that we're witnessing right now. Okay, so we're going to give an end to the show run of the autonomous vehicle, Pilatus. Now I would like to thank you all for assisting to the show run of Pilatus Driverless, and hand over to my colleague who will present the show run for our electric vehicle, Alvier. Thank you very much.
Thank you, Adria. Hello, everyone. After just witnessing Pilatus on track, I'd like to welcome all of you to the live show of the electric team, this time with a driver. A warm welcome to our sponsors who are able to join us in person, but also friends, family, and all other interested people joining us from home. Our show run will take about 6 or 7 minutes. Driving for us today is Desiree Blumer. She's a professional driver and also studying at the University of Applied Sciences in Lucerne. My name is Martin. I'm responsible for the motor controllers. And I'm going to talk you through procedures on the car and some more general information on different subsystems while driving. Our car Alvier, which you got to know during the presentation before, was developed over the past 2 years. 36 focus students were working full-time together with 22 freelancing students over the course of 2 seasons, which is adding up to a total of 58 people directly involved in the process of building Alvier. As you can see right now, the tractive system active light is illuminated in green color, meaning that the voltage on the car is below 60 volts. In our case, it is 24 volts and below. The master switch is activated, leading to the boot up of the different systems on the car. For example, our electrical control unit, responsible for all the communication on the car, together with all actuator commands and signal processing. Motor controllers, which are making sure our car is able to drive, are also part of our boot up. When the boot up is done, which should be right about now, we are able to activate the tractive system master switch. The tractive system refers to the parts of the car with a voltage over 60 volts. This allows us to connect our high voltage accumulator to our inverters and get the car in the ready to drive state, which you should have heard by now. Together with the driverless team, we have set up a short circuit where we are going to drive for the next couple of minutes. I'd quickly like to mention our dynamics crew responsible for the car tonight and during testing on different tracks throughout the week. Usually we try to mix up our squad once in a while so different jobs can be done by multiple people. Before driving, we need to check all the systems on the car and then give a go-ahead. Since our team consists of mechanical and electrical engineers, we split up the tasks in such a way that everybody contributes to a smooth process. We check all the screws, bleed our suspension, test our electronic components, and mount aerodynamics devices that are not on the car during transport, such as our front wing, and we make sure that the motor controllers are working properly. The wheels are only mounted when all the steps above are passed and the car is ready to go on track. Depending on the weather conditions, we are either choosing dry tires or wet tires. Since the conditions are dry, we opted for the dry tires for tonight. They have a slick surface and therefore maximize the contact surface with the ground, which leads to maximum grip. For the show run, we are using 4 of our self-developed 10th generation motors. Every wheel has its dedicated one. They are controlled separately by an inverter, which we develop ourselves in the 3rd generation. What we basically do is detect how much pressure is applied to the accelerator pedal by the driver and then calculate how much torque results for every driven wheel. To achieve this, we invert the direct current from our high voltage accumulator to alternating current for our motors by opening and closing switches in a specified time frame in order to generate a sinusoidal waveform. In order to prevent wheel spin, we have a traction control system which assures us that the angular velocity of our wheels does not exceed the limit where we would experience spin. This is really important since Formula student tracks are built in a way that straights are no longer than 75 meters. Hence, we need to accelerate and decelerate a lot. And without wheel spin, we can improve our performance on track by a huge margin. What you can see on our rear wing is a drag reduction system, which allows us to reduce drag on straights. On a straight line, we have a combination of a minimum of lateral forces combined by less drag due to the drag reduction system. This also allows for a faster acceleration. Like most of our features, this is directly accessible via the steering wheel, so the driver can choose whenever to apply systems on the car. Other examples of systems the driver can manipulate are active ride height and rear wheel steering. Active ride height enables us to shift our center of gravity up or down depending on the situation we're in. Rear wheel steering allows us to actually steer the rear axle by up to 3 degrees. During the whole run, all the different sensor signals such as motor temperatures, velocities, estimations and driver inputs are recorded so that the team is always able to analyze the runs and improve the settings on our car. This allows us to get a better understanding of different parameters and their influence on performance. With our inertial navigation system, we are even able to reproduce the exact map of driven tracks so that we are able to analyze the data compared to different scenarios while driving. I really hope you enjoyed this little small talk and I could talk you through a small part of what our car is actually capable of. Sadly, we are now slowly but surely coming to the end of this year's AMZ Rollout. In the name of AMZ Electric and AMZ Driverless, I would like to thank each and every one of you for attending in person or via live stream. A special thanks to our sponsors for their continued support in those difficult times. Without you, we would not be able to pursue our passion and build those amazing prototype race cars you were just able to witness on track. Due to strict COVID regulations, we will have to follow a different procedure compared to previous years. We kindly ask everyone to keep the distance, not gathering groups, and leave the area as fast as possible. Thank you for coming and enjoy the rest of your night. Good night.